Okay, good morning. So my name is Ion Stoica. I am a computer science faculty at UC Berkeley, and I am one of the co-directors of the AmpLab. And welcome everybody to AmpCamp 3. So to put things into perspective, a brief history. So we had the first AmpCamp 1 year ago in August 2012, and it was more successful than we expected. We had 150 people attending in person and over 3,000 people online. Then we have the second AmpCamp 2, and we ran this as a full-day Strata tutorial in February 2013. And this was also quite successful. The hands-on portion of the tutorial was sold out. So here we are at AmpCamp 3. We are having this today and tomorrow. And we have already 250 people. It's everything. All the seats are sold out. So thanks, everybody, for making this, which we believe, another success. And just to make sure, and we didn't time this to coincide with the closing of the Bay Bridge. So in the rest of the talk, I'm going to discuss three things. First, I'm going to look at the big data problems we are targeting to solve. Second, I'm going to talk a little bit about the AmpLab, which is the lab within which we are doing this research. And finally, for most of the time, I'm going to talk about the Berkeley Data Analytics Stack, or BDAS, which is the main deliverable of this lab. So in order to understand what is the problem, we need to understand how the data is used and what is used for. So what is the big data used for today? So for once, it's used for reports to track business processes, transactions, and so forth. Then it's used for diagnosis to answer questions such as, why is a particular service slow? Why is the user system engagement dropping? Or maybe to detect spam, worms, online banking fraud, and things like that. But most importantly, people want to use big data to make decisions, such as personalized medical treatment, decide what features to add to a particular product or service, or the classic example of our times, decide what ads to show. So much of our research is driven by the belief that data is only as useful as the decision it enables. So what does this mean? Well, this means that we want low latency interactive queries on historical data, because in general, the faster decisions are better. We want also ability to have low latency, to perform low latency queries on live data. Why? Because decisions on fresh rather than stale data are, again, in general, more valuable. Like, for instance, if you want to detect a denial of service attack. And finally, we want to support sophisticated data processing. So many of these decisions involve far more than a simple SQL query. It may involve graph-based computations, machine learning algorithms, and so forth. So we need to easily support this kind of algorithms. So in summary, our goal is to support batch, interactive, and streaming computation, and to make it easy for the users to integrate these computation models in a single stack. Furthermore, we also want to make it easy for the user to develop these sophisticated algorithms which are required for many of today's decisions, such as graph machine learning algorithms. So I mentioned in the previous slide, actually in previous two slides, a few times, actually, implicitly, the need for this unification. So why do you care to unify, to have a stack which provides you support for streaming, batch, and interactive computations? So I'm going to use two examples to illustrate this need for unification. So the first is like, let's take a look at a state-of-art analytics stack today. So what do you have? You have a bunch of logs you are going to collect, and typically you may push these logs into a Hadoop stack. And then once the logs are there, you can perform complex, arbitrarily complex ad hoc queries on this historical data, but of course they are quite slow. Now, people in general also would like to have access to be able to do interactive queries, even though they trade the sophistication of the queries. So what do people do? Well, they take that data and they push to another system maybe, or use another system, like Impala or a SQL, MySQL, a SQL database, or maybe they use HBase. And more recently, people start to add to their analytics stack a real-time, a streaming component, for instance, based on Storm, to provide real-time analytics. Okay, so this is how it looks like. So what are the challenges here? Well, the challenges here is that you need to maintain 3 systems, like, for instance, Storm, Hadoop, and maybe Impala. Okay? This is kind of expensive and quite complex to manage all of them. And also, there are other hidden costs. Like, for instance, presumably, the Hadoop stack and the streaming stack, they are going to compute the same metrics. Now, you have 2 software implementations which you need to maintain and make sure that they are consistent with respect to the metric computation. Right? So this is kind of hard. And finally, it's hard to, and in some cases slow to share the data across the stack. So for instance, you have a MySQL database you use for interactive queries. You need to put the data in that database. Here is another example. So more and more people, they want now to make real-time decisions. So let's take like for detecting, say, fraud or in online banking or online transactions and denial of service attacks. So let me take, what do you need for that? So let me take as an example the denial of service attack. So first, you need to you need to detect a pattern, the attack pattern. Maybe this is just as simple as a surge in the traffic, right? And you want to do it as soon as possible because, in seconds, if it's a denial of service attack in the internet, that can already affect millions of machines, right? So you need to be fast. So what do you need for that? Streaming, right? But then you need to make sure that you see an unexpected surge that maybe that's actually not an attack, but maybe something periodic, structural. Like, for instance, diurnal pattern. In the morning, people wake up, check their email, right? Or maybe it's a weekly pattern. So in general, you want to look also in the past, temporary, to make sure that this is indeed an attack. So what you need for that, because again, you want to make decisions fast, you need interactive queries on the past data. And finally, you want these queries to be very fast, right? Because you still want to make the decision and decide in real time whether it's an attack or not. So in order to make this query fast on the past data, what you typically do, you take the data, right? And actually you do some pre-computation to make the queries fast. A simple case of pre-computation is indexing. This is basically batch, right? So it's an example in which, for solving this problem, you need streaming, interactive, and batch computations. And of course, you need, at least in this case, to implement probably complex algorithms, because for anomaly detection or this kind of detections, simple algorithms maybe are not good enough, so you may need machine learning, some machine learning or other statistical algorithms. Okay? So this is basically why we put a high price of the unification of these computation models, and you'll see also the programming models. So we do all this work to address these challenges in the context of the Berkeley AmpLab. Okay? So Berkeley AmpLab started in January 2011, and it's a 6-year effort, so we are at half of this effort. And it consists of 8 faculty in system, databases, networking, and machine learning. It has more than 40 students and postdoc, and we also have a 3 software engineer team. And the AmpLab, the AMP comes from algorithms, machine, and people, and this is because we plan to use this holistic approach, algorithms, new algorithms, machines, new systems, and people crowdsourcing to address the big data problems. In this talk, I am mostly going to focus on the machine side and a little bit on the algorithm side. The AmpLab is organized for collaboration. This is a very important aspect of how we run this lab. And here on the left-hand side is a floor plan. It's an open floor plan, like you find in any startup. Even more, the faculty are sitting in an open space, in the open space as well. So we don't have offices. So this really drives a lot of interaction. And here you see the people, again, system, networking, databases, machine learning. It's all this area. And of course, we run also a 3-day retreat twice a year. Many of you attend those retreats, in which we present our newest research and we get feedback from the industry. And the AMP camps. This is a picture from the AMP camp 1 year ago. So how are we funded? It's a governmental and industrial funding. We got both of them. We have multi-million, multi-year contracts, grants from NSF and DARPA. And of course, we get a lot of support from industry. Amazon, Google, and SAP are our founding sponsors. And we have another 18 sponsors and affiliates. The main goal of the AmpLab is to build this next generation of open source data analytics stack for industry and academia, Berkeley Data Analytics Stack, or BDAS. Okay, and this is what we are going to talk about today and tomorrow. So again, to put things into perspective, how does a data processing stack look like? So it looks something like this. You have a storage layer, you have a resource management layer, and a data processing layer. So let's map this onto the Hadoop Stack most of you are familiar with. So the storage layer, you have HDFS or maybe S3 or something like that, right? A distributed storage system. Then recently at the management layer, you have Hadoop Yarn, which allows you to build to run multiple instances of frameworks, being Hadoop, MapReduce, or maybe others. And the data processing layer, you have a bunch of cluster computing frameworks, starting with Hadoop MapReduce, which on top of it, people run Hive and Pig to provide some SQL capabilities, then age-based Storm, and so forth. Okay, so this is how it looks like. Now, how does these 3 layers map? How does our stack maps on these layers? As a storage layer, we are still using HDFS and S3, but we also have an addition we are working on Tachyon, which is in memory storage layer, which allow different cluster computing frameworks or application to exchange, to share the data much faster. As a resource management layer, we have developed, starting since 2009, Mesos. And as a data processing layer, we have also a bunch of frameworks. And Spark is our, so to speak, narrowest execution engine in this data layer. And on top of it, we have a bunch of frameworks which provide different capabilities. But all of them are using Spark execution engine. Now, you may ask yourself, okay, you build a different stack, so why don't you go and build the Hadoop, improve the Hadoop stack? This is one question we get quite a bit. So let me not address that question right away. What I'm going to show is that actually these stacks actually fit well together. So if you look at this image, you can actually Spark doesn't require to run Mesos to run. You can also run on Hadoop Yarn. Actually, this support has been dramatically improved. It will be dramatically improved with the next release, which is days away. At the same time, Mesos doesn't run only BDAS frameworks. It also can run Hadoop MapReduce, and Storm, and other frameworks. Okay, so this is how, and all of them, we can share the HDFS storage. So this is how it fits in. Now, in the remaining of the talk, I'm going to take the BDAS stack, which you see there on the top right, and I am going to briefly describe the components, the main components. And actually, you are going to hear later in the day and tomorrow talks about these components, and you are going to have the opportunity to do hand-on exercises using these components. So let's start with Mesos. So Mesos, it's Apache, it's an Apache project, and enable multiple frameworks, cluster computing frameworks, to share same cluster. So you can have multiple instances of Hadoop, Storm, Spark, sharing the same cluster. It's a pretty mature software right now. Twitter is the largest user of Mesos. It runs it of over 6,000 servers in two data centers. In each center, you have over 3,000 servers. There are more than 500 engineers running jobs on Mesos today. There are already third-party Mesos schedulers being released, Airbnb Chronos a little bit earlier, and Twitter's Aurora more recently. This is proposed. Aurora is for Apache incubation. And also, recently, a startup has been created, Mesosphere, great name, to commercialize Mesos. Okay? Spark. So Spark is our distributed execution engine. So in the Hadoop world, you have the Hadoop MapReduce as being the execution engine. In BDAS, you have Spark. Spark has a fault-tolerant, efficient in-memory storage. This is one thing it provides, and it proved to be very powerful. We call that abstraction resilient distributed data sets, and you'll hear more after the break, after this session. And it provides a very powerful programming model and APIs. It has APIs you can program in Scala, Python, and Java. Because it's it has many, it's using a memory, it can perform in-memory processing, and also has a much more efficient and low latency scheduler and other improvements. It's fast. It can be up to 100 times faster than Hadoop. It's also easy to use because it's a very powerful programming model which goes beyond MapReduce. And in many cases, the code for the same application you'll write in Spark is 5 to 10 times less than in Hadoop. And in general, in that it provides support for interactive and iterative applications, again, because the data is in memory, it's fast to query if the data it's in memory, and also for iterative computation, the iteration can share the data between themselves across through memory as well. That's what makes it fast. Since last MCamp, there have been 2 major releases. And the next release will be, it's like I mentioned, days away. Spark streaming, it's a component on top of Spark. Actually, it's a component within Spark. You get it on downloading Spark, and it provides large-scale streaming computation. The interesting thing here is the way we implement streaming. Typically, the streaming, you run some operators, stateful operators. You organize them in a DAG, direct acyclic graph. The data comes in, and they are consumed by these operators, and another data or tuples are generated and go to other operators in this DAG. And this is a good design. However, it has challenges to deal with failure, with slow nodes, and things like that. So Spark streaming takes a very different approach and leverages the ability of Spark to run sub-second parallel jobs. That's what it runs, what it uses. And it uses that ability to implement streaming as a sequence of batch jobs. Each batch job is runs very, very fast, in hundreds of milliseconds. So this batch job incrementally updates the state. So therefore, you get this streaming functionality. The advantage of this design is that because you use batching, that's fault tolerant. like Hadoop, handle stragglers, again, similar like Hadoop, and also ensure exactly one semantic. Now, if you add Spark streaming to Spark, now you have support for batch interactive and streaming computations. We already have an alpha release of Spark streaming, which receives considerably attention, in particular more recently. The next component, and this runs on top of Spark, is Shark. So Shark fundamentally it's running Hive over Spark, so provides full support for Hive QL and user-defined functions, Hive user-defined functions. So you can take your Hive queries and you can run on top of Shark. Why would you want to do that? Because it will be much faster. If the data is in memory, it can be up to 100 times faster. And even if the data is on the disk, it will be between 5 and 10 times faster because we use column-oriented storage and many other efficiency improvements in the scheduling, in the data communication we made in Spark. It's running today on hundreds of nodes at Yahoo and many other companies. And there are two major releases. Along Spark since the last AmpCamp. So I mentioned to you about, you want to provide this kind of generality to unify these various computation models. And of course, a question which I answered a little bit is that how fast are we compared with specific, with domain-specific frameworks? So the answer here is that in general, we are pretty fast. So it's not like, not only that to unify this computation model, we are also fast. We provide good performance. So here is for interactive computation, is that Shark, it's significantly faster than Hive, and even than Impala when the data is in memory. For batch, here is an example of machine learning algorithms, and this is how long it takes per iteration. It's at iteration time. This is for logistic regression, and Spark is 2 orders of magnitude faster than Hadoop, mainly because the data between subsequent iteration is shared through memory instead through disk. And finally, streaming. This is a comparison with Storm. So this is throughput. So previously, lower is better. Here, higher bars are better. It's very competitive. Spark streaming is very competitive with Storm. We unify not only computation models like streaming, batch, and interactive, but also unify the programming models, right? So we provide, we allow unified systems for SQL, graph processing, and machine learning to run on top of Spark. And here you see on the top right, you see logistic regression snippet, implementation of logistic regression in Spark. And in the bottom right, you see how a user uses a SQL command to select a table of users, then on which to run logistic regression. So you can do all of this in one application. It's very powerful. So these components, leading with Spark, are gaining rapid traction. I mentioned about the AmpCamps we had so far. But the one thing we are really excited now is that we see a lot of contribution, external contribution. So there are more than 20 companies and more than 70 individuals contributing back code to Spark and other components. The meetup, Spark meetup, now the number of users is over 1,000 people and grows very fast. So just to give you a sense, at the beginning of June or the end of May was 700. And last year when we had this AmpCamp was 300. So the growth accelerates. It's also, it's Spark and Shark. Now you can run them on Amazon Elastic MapReduce. So they host the scripts to run Spark and Shark. And very recently, one Disco announced support for in-memory for both Spark and Shark. So next I'm going to briefly talk about the other components. You are also going to hear and do some hands-on exercises using these components. So BlinkDB. So BlinkDB sits atop Shark. So why do we do that? So the reason we do that is, again, we want to have, I told at the beginning, very fast, very interactive, support interactive queries. And of course, you say, OK, you put data in memory, everything will be fast. Well, it turns out that if you have the data in memory, it's not necessary that everything will be fast or as fast as you want. So here is the architecture of a node. Today, in a high-end node in a data center, 512 gigabytes of RAM, maybe have a 16 or 24 cores. And then the bus bandwidth is between 40 and 60 gigabytes per second. Maybe the new ones will get to 90 gigabits per second. The point is that even not doing any computation, just scanning this memory, it may take 10 seconds. And here I ignore any contentions. So this is not good enough for an interactive query. So BlinkDB enables the user to trade between query performance and accuracy using sampling. Okay? And it's, again, the need for this is emphasized also by the fact that the memory storage increases faster than the memory bus. So this problem will be exacerbated in the future. So the key insight in using BlinkDB, in developing BlinkDB, is that the input you get and you operate on is often noisy. You get the logs. Some logs are lost. Some logs may have include metrics which are computed with some error, and so forth. So in most of the cases, even if you can perform exact computations, it does not guarantee you exact answers, because the data has some noise to start with. And the second insight is that the error, often acceptably small and bounded. We are operating today with many devices which have an error built in. Your speedometer in your car has 2.5% error. The main challenge in BlinkDB is to estimate error for arbitrary computation. We just have an alpha release 1 or 2 weeks ago. And this is a pretty basic release which allows users to build uniform and stratified samples and provides error bounds for simple aggregate queries. But here is an example to illustrate the use of this, of BlinkDB. And real data from Conviva, which is a company which manages video distribution in the internet. And here we are looking at, the data is anonymized, of course, at the worst performers in terms of quality. The quality here is measured as buffering ratio. You know, how much the video buffers. And they are grouped by city and ISP. The data was, the data input data here was 17 terabytes. And it takes a Hive query, I think 100 instances in EC2. It will take to run 772 seconds. Now we run the same query, but now we want to get a response time in 2 seconds, not 773 seconds. And what we get, we run on a sample which is 1.7 gigabytes. So it's basically one machine. We'll have enough memory for that. And the query runs in less than 1.8 seconds. And there are 2 points to notice here. First, you have some errors. You know, if you look on the rightmost column, there are some errors associated with the results. But the ranking of the top 10 worst performers is the same. It's identical. The second point is, of course, if you do compute use a sample, it's 440 times faster. GraphX, it's a component we are working on, and we expect a release this fall to support graph-based processing. You know, there are a lot of social graphs today. You want to make a lot of computation on them, so GraphX tries to fill that need. And it combines the data parallel computation and graph parallel computation models and provide very powerful abstraction. For instance, we can implement the power graph and Pregel using less than 10, 20 lines of code. It leverages sparse for fault tolerance, so therefore you can share the data with Shark or sparse streaming and so forth. You can get the data streaming in, and then GraphX can take and try to analyze in real time. Not finally, next to last, this will be one of the most important projects today in the AmpLab, and it will continue to remain very important. Actually, its importance will grow in the future. It's machine learning. So we are going to very soon release a MLlib, which is a high-quality library for machine learning algorithms. But the bigger project and the more ambitious project is MLbase. And the goal of this project is to make ML accessible to non-experts. It uses a declarative interface to allow the user to say what they want, not how to do it. Like, for instance, the user say, OK, classify this data. The MLbase will automatically pick best algorithm for a given data and a time. So during the running time, it may switch between the algorithms dynamically. And the first component of MLbase will be released, MLI. It will be released also in September 2013. We'll have a talk about this tomorrow. Finally, the final component I'm going to talk about is Tachyon. Tachyon is an in-memory fault-tolerant storage, which provides flexible API, and including HDFS API. So this means that Hadoop can also use Tachyon. And of course, the advantage is that the data fits in memory, it will be faster. We have an alpha release. It was in June 2013. And some companies already are planning deployments of Tachyon. You'll hear a talk about Tachyon tomorrow. So now we build all of these components and this stack. And again, I want to emphasize, in doing so, we tried as much as possible to be compatible with the existing ecosystem. And here I'm just going to show a few layers of compatibility. Sparse streaming accepts inputs from Kafka, Flume, Twitter, TCP sockets, so a variety of inputs. It's very easy to write a new driver to accept a new input format. Shark provides, like I mentioned, Hive API, so you can run unmodified Hive queries. GraphX will provide Graph Lab API if you are, it's a very popular graph package. Mesos, like I mentioned, provides support also for Hadoop MapReduce framework, Storm, and MPI. And Tachyon, like I just mentioned, provides also HDFS API. So in summary, within the AmpLab, we developed the Berkeley Data Analytics Stack, or BDAS, to address the next big data challenges. And one of the key of our approach is to unify the batch, interactive, and streaming computation, and to make it easy to develop sophisticated applications by using, by supporting graph, machine learning algorithms, and also providing support for approximate query processing. We are witnessing a significant adoption of some BDAS components, at least the more mature ones. It's also a vibrant community, development community. There are more than 20 companies contributing back code, and more than 70 individual contributors. And as you look forward, there are a slew of very exciting projects we are working on, and you are going to hear about MLbase, GraphX, and BlinkDB. So now, before ending, just let me give you an overview about the rest of the AmpCamp. So the rest of this session, you are going to hear 10 minutes about the curriculum, and then a talk about Mesos. Then from 10:45, you are going to hear talks about Spark, an introduction to Shark and Spark streaming. And then, with that knowledge, after the lunch, we are going to have hands-on exercises on Spark, Shark, and Spark streaming. At 5, we are going to have a user presentation, the use case scenarios. There will be from Conviva, Oyala, and Yahoo. And we are going to end up the day with a reception at 6:30. Tomorrow, you are going to hear talks about BlinkDB and MLbase. followed by a hands-on exercise on BlinkDB MLbase, and also we are going to add the mix in the mix Mesos. Then, in the afternoon, we are going to hear talks about introduction to Tachyon and GraphX. And we are going to wrap up at 3:15. Any questions? Okay, this will help us keep on track. So the next, yes, sorry.
Are you going to have multi-track for the hands-on exercise, or is it the whole room in one day?
Andy will answer that question and more.